Okay, I think we are ready to start. And today we have a lecture number 3 of our class of machine learning techniques and structural mechanics. And let's first briefly recap what we learned from the previous lectures and practices. So we learned that artificial neurons is the core element of almost all neural networks. That's true. Neuron performs linear transformation of the input data and subject the results to nonlinear activation function. If you remember, that was very important part. Without activation function, we cannot learn nonlinear relations between inputs and outputs. It's quite true. And we also probably will see another example today why it's important to use some nonlinearity, but in a context of support vector machines. We also learned that the most important and in many cases secret component of neural networks are their weights. And actually, I found from OpenAI report release strategies and the social impacts of language models. Basically, OpenAI is the guys behind all this ChatGPT. And when they proposed GPT-3, if I remember correctly, they roll out the model step by step, or maybe it was for GPT-2. So first they open access to the model with a few weights, so not so accurate model, and then gradually they assess how society accepted that. They saw some bias, so they change the training a little bit, then they release the next iteration, and finally, I don't remember, I think it actually in 2021, they released the final version of ChatGPT 2 with weights, and you can download it. But in many cases, weights are secrets. So, for instance, we more or less understand how ChatGPT works, but we have no idea about the weights of the neural network. So that's always secret component, and that's what you need to protect if you're running AI company. So what we also learned, that we search for the appropriate weights during the training stage, and we actually practice it a little bit during the practice. Depending on the input and output, we might have supervised and unsupervised learning. Again, if you remember the examples, when we have output labels labeled for us, then we have supervised learning. If we don't, we have unsupervised learning, and we try to do this so-called feature detection. And for supervised learning, we usually have two different types of tasks, classifications and regressions. And here, basically, depending on our output, we can select either its classification or regression. So from the practice, we also learn to be careful with the lists in Python. I remember a lot of interesting results with the lists in Pythons. We also learn a little bit how to define simple neural network in TensorFlow. What stages do we need to go through? We learn the importance of the activation functions again. We more or less understand, but we will repeat that next session as well, what is training, validation, and test data sets, and why it's really important to separate them, why it's really important to hide some of your data from machine learning, from the neural network, in order to then verify how good it performs, how good it generalizes everything. And also with that in mind, we also learned a little bit how to evaluate the performance of the trained model. If you remember the lines when you run the fitting, you have this test data set loss and validation loss, and you can see how well training goes and what's performance of the neural network afterwards. And we actually will talk about that right now. So how do we know that our model is good? So when we train something, we at the end would like to basically assess how good the things that we are training. And what would be your answer on this question? How do we know that our neural network is good? Okay, that's very, very scientifically. Can you make it a little bit more for just general public? So how do you do that? Okay, Okay, so you actually put a lot of there in this basic reply. You touched a lot of different topics, and actually we will do step by step, but it's actually correct. So obviously by comparing predictions with true values, especially for the problems when we have labels, we really need to compare it with our true values. And here I have a quite interesting example for you. This is a paper in Physical Review Letters from October 1941. And I intentionally censored some words in the title and in abstract, something pure metals, copper, gold, aluminum, nickel, and iron. And then in abstract, you can see that extremely accurate determination of the blank have been made, and then following. And then I actually discovered this table inside. So we have a temperature, and we have some value that we, again, I had censored for you, that basically associated with the temperature. And for now, what different physical things are associated with the temperature can you name? So at least something. So what depends on temperature in real life? From material science, mechanical engineering. Hardness, right? Stiffness, yes, you have this melting. Density, yes, as well. Okay, also conductivity depends. So you have superconductive materials if you go very, very close to zero. So basically, that's one of these elements. And now I was bored, and I decided, okay, let me plot these values, like type them and plot them, and that's what I got. So I have this temperature here. I think it's in kelvins. Yes, I'm pretty sure it's. I know, actually, it's in Celsius, and I started from the room temperature. So because with the negative temperatures, it was really hard. And again, I blanked this value here. We don't know that. And now my question is, how good are these measurements? What do you think? Just on a scale from 0 to 10, 10 is the best, 0 it's absolutely atrocious. Okay, give it a grade. From 0 to 10. 8, 9, okay, good enough. So then, what you will say about this data? How you will grade it? Okay, so I will give it maybe 5, 4. Well, let's say like that. But now I give you a trick question. What about this data? How do you believe me that actually this is the data from the table and not this is the data from the table? How will you grade this data on the right? How good the measurements are if you look at the right? I would also give it probably 8 and 9, right? Because it looks okay. If I would hide this one and ask you to evaluate this one, you will say, okay, this is a good data. And so no, that's tricky. Is actually, I think I see that you're kind of you are not comfortable with that, and that's because we can answer only if we assume specific model. So if kind of we expect some linear behavior and we see like quadratic function, that means that our measurements are not good. If we expect linear and see linear, that expects that we are okay, so we are good. Of course, there is some minute details there because you can also estimate just real variance in the measurements, and you expect in physics not to have so much chaotic behavior. At the same time, there are examples of the chaotic systems for which this behavior would be absolutely ideal. That's exactly how they behave in real life. It's rare, and of course, we kind of expect it to be more smooth, but in general, you cannot discard that based on just how it looks like. When you compare it with something, then you can say that. And actually, this secret measure was relative elongation of the metallic rod. So basically, what they did, they put a metallic rod, cool it down to almost minus 200 centigrades, and then heat it up and measure how it's actually expanding. So of course, it's not dL by L; it's also multiplied by 10 and minus 6. Otherwise, it would be ridiculous. So what they measured, and that's actually quite accurate measurements, and that measurements actually match the theory very well because you expect your expansion to be linear. So That's why it's really important to have something in mind when you compare it. Not just look at the data, but also to compare it with something. So, and also what we can do in this case, for both of these situations, we can say, okay, I will put a line here and here. And now for us, it's obvious that these data are better than this data. And again, which one is better? And we need to introduce some measurements of goodness, because when we do this grading, we kind of do it intuitively, but now we need to do it more or less formally. So what we do, we introduce a new measure. But for that, we first need to look at the experimental data point. So we have xi and as the temperature and yi as the elongation here. What we also can do when we, let's say, we have our model, yes? So, and predictions in the model usually denoted as yi with a hat. So we have some function f that we are trying to understand how good this function is for our data. So for each xi, besides of already known experimental result, we introduce yi with a hat, and then we calculate the differences between them. So what would be our next step? Because right now it's not enough. We can look at the differences, but we need to kind of combine everything to one nice grade. What we do first, we do an average of our experimental data. So this is average over n experimental data points. And then we introduce two parameters as residuals and total. And basically, this is the squares of residuals. And total, it's square deviation from the average obtained in experiments. So basically, this is only experiments, so you see no predictions here. And this part actually takes into account predictions because there is a subtraction. And then we introduce so-called R-square score as this one. 1 minus ratio between SS-res and SS-tot. And if you will look into the machine learning problems, machine learning papers, you quite often will see these measurements to understand how good your model is in relation to the data that you have. And for your reference, this R squared here is 0.99916, and this one is 0.90. And what's the limits, in your opinion, for what's the brackets for the score R, in your opinion? So what's the maximum R? It's 1, yeah, because it will be 1 only if this residuals will be 0. That means that all components should be 0. And what's the minimum value? Yeah, it's 0. It can, yes, it's 0. It's actually quite rare to have 0, but yes, you need to be very random, basically ideally random to get 0. So just as a small exercise, because you will see a lot of data in general when you will work with machine learning. So as to see how fast this R score drops, I just draw a couple of examples. So let's start with, here we already know this. What do you think approximately the R score here? 0.90. Which one is this one? 9.8. So yeah, this is 9.0. I would honestly, from the training point of view, from the machine learning, I would consider this is already, it's still good case, but it's already probably you need to invest a little bit more time in your training. This is also kind of yes, but at the same time, yeah, definitely. And these two examples basically shows very little correlation. So I would say this, if you see something like that in your training, comparison between training and true data, that means that something is going wrong, and I would not recommend to publish that at all. So top row is good, bottom row, it's you need to work a little bit more. So with that in mind, basically when we introduce this R square score, we kind of introduce the concept of loss function or cost function in some way. So because if you remember from the practice, when we do our training, we track the loss function. Now I need to be specific because in literature, sometimes authors separate loss function and cost function. and many other cases, they are not. So here I will use these terms interchangeably. Basically, if I say loss function or cost function, that means the same. Kind of there is a small, basically, reason to separate them. Sometimes people are saying that loss function is the function that is computed on one sample, and cost function is something that's computed on whole data set, but it's so super arbitrary. So I would say, okay, we will ignore that and we'll use these two terms interchangeably. So, and selection of the loss functions, and again, we practice that, depends on the problem. So let's talk first about, this is a bit wrong. We will start with regression problems, because I wanted to start with classification, but then I realized it would be probably a little bit more interesting to start with a regression problem. So, I can actually probably do something like that. So if we look at the documentation for Keras or for TensorFlow, we'll see some of the regression losses already implemented inside, so you don't need to write them from the scratch. And among them, we see mean squared error, mean absolute error, mean absolute percentage error, and mean square logarithmic error class. And we will actually take a look at all of them. And that's how they, wow, nice weather. That's how we define them. So mean, yeah, if it's splashing, it's better to close probably. Freiburg. So basically on the top line, we see mean square error, right? And this is something that you should be familiar with already. So we take our real data, real sample, we have n samples, n points. This is a real data, like basically true data. This is a predicted data, and we calculate the mean square error. So alternative of that is to look at mean absolute error here. So instead of square, we take the absolute value. Technically speaking, it's also possible. Very interesting loss function is this mean absolute percentage error that you see here, MAPE. And as you can see, there is, of course, 100%. There is, of course, averaging over the number of samples. But inside, you have a very interesting thing. You look at the difference between real data and predicted data and divide it by the predicted data. And actually, you will see why it's maybe important when we will talk about the last function. But now I would like to challenge you and ask you, do you see any problems with this particular function? Why it may be problematic to implement that and work with that? Any ideas? Yes, from one side, yes, but at the same time, it's not the biggest problem, to be honest, with this particular function. We will address that when we'll talk about the last one. But there is a more obvious problem with this particular function. Yeah, the problem not even with the small values, to be honest. Yeah, the problem is with what to do if the denominator is 0. Then you have a problem. So you need to always take into account and actually, I think, add. It will not work here. Like you may think, okay, I will every time add something small, like some value like that. But at the same time, what if your prediction would be equal to negative value? You have 0, and then you need to check. So therefore, you will almost never see this function in use. So it's actually quite useless function. At the same time, the bottom function that you see here, it's much more interesting. You still have a problem with zeros, possible, but in this case, if you add some value, you're usually good. Why this particular function might be even better than this one? Do you see it? Can you assume why the logarithmic measure is better than just regular measure? Any ideas? In general, when we use logarithms, Basically, that's absolutely right. And a good example of that, if I will take, for instance, okay, I will take this one. Let's say I take the number 1. It's my real data. I have two measurements, and I have my prediction data, it's 2, and also I have my real data 101 and another 102. If you take a look at the first measure, mean square error, what you will see that basically it's the same. So 2 is the same, like 2 and 1 have the same difference as 101 and 102, and it's obviously not true. So if in your data set you have like values of 1 and 101, you need to think about using logarithmic measure. But at the same time, if you actually have this data in your data set, you first need to think about normalization of your data set, because it's a very bad idea. And next lecture or next practice, we will talk about that, about normalization. And also you will see that in your home project that I uploaded a couple of minutes ago, that normalization and renormalization of data is extremely important. If you have the values of the different scales, you have a problem, because your loss function may focus on the large data only, because kind of for loss function, it doesn't really matter at what scale you're working. So that's basically example why when the second function may be very good. So what I had, actually that was designed specifically for that. So now there is interesting case of classification. Finally, we go to the classification. And in classification and Keras on TensorFlow, you can see already implemented probability. They're called probabilistic losses. It's called so-called binary cross entropy, categorical cross entropy, and sparse categorical cross entropy. And if you remember, binary cross entropy, it's exactly loss function that we used in our problem with the safety or non-safety of the system with the springs. So, and it looks like that. It looks quite ridiculous, but actually I already explained it during practice. I would like to do it again here, why this is a very, very cool function. And this would be only one example, because later in this lecture you will see much cooler consequences of this function. First question that I would like to ask you, why minus? Because in mean square error, we actually have no minuses. We just have the difference. So, and therefore, what's the minimum value of the, if we consider mean square error loss, what's the minimal value that we can reach? 0. Cool. Why here we need minus? Almost, but not. So it's actually not, that's a trick. This function doesn't move in both directions. That I think. If you remove minus, this function will go from minus infinity to 0. You can get positive number here. And again, why this is very cool thing, because in classification, we remember that our labels can be 0 and 1. We consider only binary classification, so we have 0 or 1 as labels. And if you remember from the practice, when you do training, you basically never get 0 and 1. You have something very close to 1 and something very, very close to 0, especially to 0. It's like usually, if you remember, it was 0.0001, something like that. And therefore, let's say that we have our label equal to 0, and our prediction, let's say we predicted 0.001. What would be the value of this function in this case? Let's calculate it. We see that actually with these predictions we are very close. So probably we should have something very, very close to 0. Let's verify that. So let's take a look at the first part. So this is our real data, and we know that it's 0. So to be honest, we don't care about this one at all. Let's take a look at the second term. So we have 1 minus this data. Label is 0, therefore this brackets is 1. And so what happens in this case with this logarithm? So we have a logarithm of 1 minus 0.001. 0.001. It's basically a logarithm of 0.999. And since I prepared, I know this one is equal to exactly this value. So it's very close to 0, but it's negative. So when we will do inversion of the sign with this particular minus, we will get our BCE for this case equal to, which is really, really small, and that means that our predictions are very good. So what will happen actually if we do it in reverse? So we have label 0, but we predict let's say 0.999. So we are close to 1. So what we will get, again, the first term will be 0. Obviously, here we have 1 as usual, and here we'll have logarithm of 0.001, and it's equal to, what is logarithm of 0.001? Come on, you don't need to use a calculator for that. How? So, and what's the result? Okay. Wait a second. What is logarithm of this value? Okay, what is okay? That's scary. Don't hit. Yeah, okay. It's -3, of course, because it's logarithm of 10 in -3, and you take the power here and there -3, and of course in this case BCE, in this case loss function, will be equal to 3, which is quite large. So that means that your predictions are not accurate enough. So that's exactly how this function works, and this is actually a very interesting function because any other problems with this function? No, I don't think so. Because you can look at that a little bit from probabilistic point of view. Because when you talk about probabilities, you are looking from the values between 0 and 1. Probability of every event can be from 0 to 1. And our sigmoid function actually goes from 0 to 1 as well. When we kind of look at the output values during the classification, we always put the sigmoid at the end and force our data to be between 0 and 1. So technically correct. I actually read it today. So we cannot say that that this function would be probability of distribution probability distribution function. So from the probabilistic point of view, from statistics, it's incorrect to say that, but actually this function is cumulative probability function of logistic distribution. So what, again, probably it doesn't mean anything for you. So what we can look at that, at this function, we can look at that as a confidence index. So if our values are close to, for instance, we can have the value here, that means that our output label will be almost guaranteed to be 1. So if we even closer here, if somewhere here, that means that we are almost confident that it will be 1. So again, that's how you look at this from the probabilistic point of view. Okay, so in this case, you can say, so if you're the sigmoid function of, say, z is let's say exactly what we are doing when we do thresholding, larger than, let's say, 0.9, therefore the probability to have the 1 as output is approximately 1. So that's, again, this is just intuitive understanding. It's not mathematically correct in any way, but it's exactly how you need to understand these particular functions and how they relate to the probability. Okay, so this is slide number 19, and yeah, good. So, and this is our function. Sorry, I forgot to put it into the screen. So you're already familiar with the sigmoid. Okay, now if I take a look at this list, I will see that there is something called categorical cross-entropy class, and I actually was a little bit bored, and I decided not to even copy this particular formula and type it manually. I just copy the picture because, to be honest, I don't think that you need to know this monstrosity here. So this is quite ridiculous formula, and that's why the question, what is that, or what is this, is a very valid question. What do you think is categorical cross entropy? What's the difference? We know that binary cross entropy, and basically when we do binary cross entropy, we have at the end of our neural network, we have when value output, right? If it's close to 1, that means that we have basically label 1, as we discussed on the previous slide. If we are close to 0, we have the label of 0. What, in your opinion, can be a categorical cross entropy? What we're missing when we do classification, in all examples that I gave to you, what was true for output values? What was the truth that we assumed? Okay, example with our, let's say, safety thing. So we have actually two choices at the end. We consider if our system is safe or unsafe. If we do some image recognition, we detect if it's exactly. We did detect if it's a cat or a dog, but of course we can, like, this is a bird, this is a horse, and therefore we have a multiple categories. And that's exactly what categorical cross entropy deals with. So right now we are not talking about selection between two values, but we are talking about selections between multiple values. And here there is a very interesting thing how you usually deal with that in machine learning. So how would you encode that into your system if I will say have the labels 0, 1, 2, or 3? So let's say cat, dog, horse, and bird. How you would do that? Because I cannot say this is a cat, this is a dog, this is like a bird. I need to somehow encode that into the mathematical definitions. What would be your suggestion? Okay, that's interesting way. It probably will work, but it's not the obvious way. So obvious, of course, is say, okay, cat is 0, dog is 1, horse is 2, and bird is 3, and then basically predict that. It's not a very good plan because at the end, if you remember our sigmoid function, we have the values between 0 and 1. And to be honest, for us, we don't have right now the function that can nicely predict the values between 0, let's say, and 4, with emphasis on, let's say, 1 or 2, because it's not enough if you will take the function that looks like that. You can take the sigmoid, for instance, and multiply it by 4. But what you will have in this case, you have this 4, you have this 0, and for 1 and 2, you have so narrow probability, basically, to get these values that it definitely will not work. Because in this case, let's say 4 it's a bird and 0 it's a cat, you almost all the time, if you arrange them, 0 it's a cat and 4 is a bird, you will almost every time predict either cat or the dog or the bird. So missing dogs and horse. But then I rename them and say, okay, 0 is a dog right now. On the same data set, you have a problem because you start to predict dogs more often. So there is elegant solution that is called one hot vector. And it basically looks like that. If you have 4 different classes, you can say the following. So for the cat, you will have 0. Okay, cat was 0, yes. So we'll kill this one. And it was bird, if I remember correctly, 0, 0, 0, 1. So you create that's called one hot vector. It's very, very important to to understand that that's how much neural network can properly be trained. Because if you represent your data like 0, 1, 2, 3, 4, you might have a problem. You will see one example probably on that. So, and TensorFlow and Keras already have implemented functions one hot, for instance, and Akira's, it's called utils to categorial. So we have, again, our array 0, 1, 2, 3. And if you call this function, what you will get basically exactly what I draw on the previous slide. Okay, so one hot is very important concept to understand, and that's super important and super useful when you train anything. So remember that and don't try to do. Come again? That's the next slide. That's exactly the next slide. So, but how you deal with sigmoid functions? Because sigmoid function, we know by definition, our sigmoid is something that looks like that. So it will be a problem. Technically speaking, you can put a vector there, and NumPy will give you some answer, but it will be quite useless. So actually, what's happening in this case, when you use one hot vector or categorical cross entropy class, you will get you will need to use so-called softmax function in your last layer, and that basically, again, similar to sigmoid, it takes the value of previous layer, that is kind of arbitrary rational number, and move it into the 0, 1 interval, but in k dimensions. So therefore, if we have 4 different categories, we will have basically the hypercube in 4 dimensions between 0 and 1. Okay, so and how does the system works? It's just basically if we have our vector, let's say z1, z2, z3, z4, and then in the last layer we actually feed it to the sigmoid functions. What we will get, for instance, for z1, we will have. And what would be at the denominator in this case? Any ideas? What does the sum means? And k is equal to 4 in this case. Okay, it will be. So that would be our, if then we basically have 4 by 4, 1, 2, 3, 4 by 1, sorry, and therefore this value will be on the top here. So for Z2, we will have the second row, third row, and fourth row. Question to you: according to the definition, what interesting behavior of the what interesting property of the final vector do we have? So this is our vector, let's say y. So it's y1, y2, y3, y4. So I will also, in this case, write it like that. What is interesting property of this vector? Why we don't have a diagonal? It's 4 by 1. It's 4 by 1. It's not diagonal. No, why? No, we are not stacking them side by side. Why are we stacking them side by side? No. So we have. So let me explain in this case how it works from the neural network perspective. So we have actually our output that basically it's one node at the output, but this one node output this vector of 4 by 1, and we have something that goes inside, right? So and at the end, this thing basically takes some number and do this transformation. So the question is, in this case, what would be the thing with this vector? Look at the formula. It's quite obvious what's the interesting property of this vector. Yeah, the sum is 1. Look at that. You normalize by the total sum. So of course, if in this case, if you do y1 plus y2 plus y3 plus 4, you get 1. So that's why it's also kind of connected to probability, because in this case, sort of you measure the probability to be in a specific class. So how usually output looks like, it looks something like that. You show the picture or show the input data to the neural network processes that, and outputting this vector, and usually it will look something like that. Maybe 0.05, 0. Let's say 99, 0.02, 0.03. And from here, you can clearly see that there is a 90% probability. So kind of, again, probabilities here. We can say that our image corresponds to the label number 2. So in this case, we consider only cases when we don't have this. Sometimes you have a situation when one image can have multiple classes. But we ignore that for now because it will be a little bit more complicated. In this case, you don't need to force this summation to be equal to 1. So, but in many cases, you really need to clearly select which particular group your, I don't know, metallic specimen. You take the microscopy of the metal and want to classify it. If it's a copper, if it's aluminum, if it's, I don't know, steel, but just by looking at the microstructure. And therefore, you can clearly do that, and you cannot have the mix between them. You can. Well, let's assume that you can. Technically, you can. So that's how this categorical cross entropy works. And with that in mind, actually, what is sparse categorical cross entropy? And that's the thing that actually I warned you about. Not to say the following, not to say cat is equal to 0, dog is equal to 1, and horse is 2, and bird is 3. Keras and TensorFlow allows you to do that. But inside, and then you use basically sparse categorical cross entropy. But what will happen inside, these actually things will be automatically converted to one hot vector, and all training will be done with one hot vector, but basically you will not see that. So you can use, again, for the simplicity, you can use this sparse categorical cross entropy by just defining the specific number of the class. But behind the back, like basically inside of the framework, it will be automatically converted to one hot vector because all training process, all softmax functions are designed to work on the one hot vector. So remember this very important concept. Okay, good. We can have a small 5-minute break because we will start a little bit different topic, which also related to loss functions, but we will actually understand what's happening during the training in a neural network. I try to avoid a lot of mathematics, and I already kind of when I upload that, I will. If you want more mathematics, I will recommend you to go to this MIT class. They have a quite good notes, but heavy with mathematics, or just to watch a nice recent video from the 3 Blue 1 Brown channel. It's actually quite good explanation, and it will intersect a little bit with what we are talking about afterwards. So right now, I really offer to do a 5 minutes break. Maybe open the windows because it's getting hot here, and then we'll continue. Okay. Same. Let me turn it on again. Everyone is back. Good. So we stop on this slide. What is training and how do we train neural network? And basically we're looking for the weights parameters. And I don't want to add a lot of mathematics in this course, but sometimes it's necessary, and I would like to do it quite easy. So how are we doing that? How we're training our data? And remember, we're actually looking at the weights, and usually we call weights like that, and we are trying to minimize the loss function. So when we do, let's say, this mean square error fitting that you're probably familiar from the other fields, what you are doing, you are trying to minimize the error itself. Or in this case, if we rename it in the machine learning context, it will be loss function or cost function. So we are nice. Okay, so, and that's, I will use J to denote the loss functions. One of the loss functions is already discussed. Okay, so, and the task of training, again, it's very, very clear to find weights like W star that will give us the minimum of this function. Nothing more, nothing less. It's super straightforward task. So, and again, probably you're familiar with this example. Who have seen this example for the gradient descent? So one of the most common methods that I actually used in machine learning training, it's already implemented in all these frameworks. It's called gradient descent. And so how does it work? So we can imagine that, let's imagine that we have only one weight in our system. So we have only one parameter. Again, this is not x and y. It's really important to understand. Right now, we are not looking for the function itself. We are looking for the weights. For instance, if our function is something like ax plus b, it's a linear function. We are not looking for y, we are not looking for f, we are not looking for x. We are actually looking for a and b that will fit our data the best. Again, very important to understand. So now we have an example. We have this w as our only one weight. Let me check actually if my recording is working. Yeah, it seems like it is. So this is our weight, and this is our loss function. And of course, they're somehow related. So usually, this is a classical example. This loss function has a minima somewhere. So in this case, minima is denoted by this red point. One very important thing to understand when I'm drawing that, when I'm drawing this blue line, I kind of assume that I know this blue line. Of course, model has no idea. So model at the beginning of training knows only this point, nothing more. It doesn't know where the minima is, what this landscape, how this landscape looks like. So just have this one point. So, and let's, for example, we will consider, because I think that mean square error is quite boring function, and this function is really amazing from a mathematical point of view, and you will see why. We'll consider loss function like that when we'll talk about the derivations. So, yeah, that was unlikely. Okay, I can do it the following way. So how the gradient descent works in general. So first you randomly, let's say randomly for now, pick the first point. Pick the first weight. It's called weight initialization. When you will actually do programming, you will see that TensorFlow already has some different algorithms how to initialize weights. Sometimes it's not recommended to initialize weight is equal to 0, because 0 it's a nasty number, and kind of you cannot divide by 0. You actually try to avoid 0, and actually if you look at the TensorFlow, and you will see default initialization gives some small random number. So you do that. You start with this number, and then you repeat the process. Like right now I'm saying while true, do. The brackets on the top in the superscript means the iteration number. So we start with the 0 iteration, so we randomly pick it. And what happens afterwards, it's you take the value on the previous iteration and subtract some interesting value, alpha, multiplied by the derivative of the previous point. And that's how you get your new weight. And you repeat that over and over again. First of all, why does it work and what is alpha? So it's quite easy to see why does it work. So let's take this point when we start. And then I'm asking you, let's basically try to compute W1. What is derivative in this case? What sign derivative has in this position? No, what sign? Is it positive or negative? Come again? Minus. It's negative. We're going down. It's negative. Of course. In this case, let's say that alpha is small, and we have some positive number here, right? Oh, negative. Sorry, negative. And since we have a minus here, and we consider alpha to be always positive, one of the important things. Therefore, we have a negative minus negative, so we have a positive number, right? So therefore, our next guess where the minima is will be on the right side, right? So we basically plus some small value. So actually, we just do that. We just basically, okay, let's go here. Then we look here as well and say, okay, this is our W1. What we can say about W2? Do we have a positive or negative? Again, we have negative derivative here, therefore we will do plus. So we again jump here. Let's think that accidentally somehow we appear here. So now, on the next iteration, what is our derivative? Or the sign of our derivative? Positive. Therefore, we will do minus. Therefore, we'll actually jump in this direction. So, and you can clearly see how by repeating this one over and over and over and over and over and over again, we will kind of go to the minima. Right? Now, my question for you, from this intuitive understanding, what is the deal with this parameter alpha? And I already told you that alpha should be more than 0. It's a learning rate. Absolutely right. You remember that again from what you did on the practice. It's a learning rate. So what happens if the learning rate is high? You are thinking two steps ahead. Don't go there. It's actually it's not guaranteed to overfit or underfit. It's actually not. So actually, what happens? Yes, we can skip the point. If alpha is very large, so we say we detect that we need to move right, but alpha, let's say, is 1, so we actually jump here. Now we jump here, and we may have a situation when we never converge. So if alpha is very small, our steps would be super small, and we will actually reach the minima, but it will be super slow process. So alpha, it's what's called hyperparameter. I already mentioned that during the practice. It's something that you need to be careful when you're picking it up. My recommendations, how I usually do that, I start with something like that. And then, depending on training, if I see it's fast or not, I actually multiply it. Basically, it's then I go if it's. So you do not multiply it by 10. You multiply it actually by e, almost, because according to some mathematical things, multiplying by e is the best way to do stuff. So that's a recommendation to, if you try to play with the learning rate, play in this particular manner. Okay, so we know right now, we actually right now understand gradient descent in 1D case. There is nothing more to understand. So now, what if we have a more than 1D? And here again, we start to have some problems. First of all, the objective is absolutely the same, but now W is already become a vector because we have multiple weights. And this is actually an example, for instance, how gradient descent works in 2D depending on your initial guess. And you actually can see the problem here, because gradient descents always try to go to the minima, and if you start next to this minima, you will go there. If you start with next to this minima, you actually will go there. So that's always a problem in any optimization, not only in machine learning. If you have a quite nasty landscape, you may have a problem because your models will converge to the different minima. Therefore, it's very important actually to properly pick the loss function. And all loss functions that I presented, they are good. They are really good. They usually do not have these problems with the multiple minima. Of course, they can, but usually they are good for that. So if you write your own loss function, and we will do that at the end of the class, we will write our own loss function. Be careful with that, because you may have a problem when your loss function is not good, doesn't have a one minima, or have a very... There is another problem that is not visible, unfortunately, in this particular example, or maybe actually it's visible if we will run it again. Let's take a look at maybe this point. You see how slow this point is here, because our landscape is almost flat, and therefore our derivative will be almost zero. So that's a problem as well. So you don't need to to be in a minima. Sometimes you can stuck on the plateau. So again, that's something to take into account. And in this case, what's the modification of the equation? We have basically nothing except this fancy thing. So what is this? Yeah, it's gradient. Again, this is a gradient. In 1D, we saw the derivative, and unfortunately, derivative in 1D, gradient doesn't work properly, because in 1D, it can be negative or positive, and that's more or less over. So what's the physical meaning of the derivative? Oh, derivative, sorry, gradient. What is the physical meaning? Come again? No, what's the property of the gradient? Physical meaning. So yes, it actually takes the derivative. So if I will take a look at this expression, for instance, what I will see this is actually a vector that looks like that. What the physical meaning of this vector? That's my question. It's very important, and I think some of you already had that in the micromechanics class. What's the meaning of the gradient? No, like in some sort of, it's not rate of the rate, it's actually a rate of the change, because it's the same as the derivative. But again, there is one very important in more than one dimensional space, especially it's visible here in two-dimensional space. Two tangents to where? No, you see, this thing here initially moves in this direction while minima is here. So it's nothing to do with minima. Gradient, actually, it's local thing. It doesn't have any idea what's happening there. So locally, what is that? It's not flux. Flux. It's more not gradient in this case, but divergence. Come again? Yeah, it's not a flux. Again, this is more divergence. Like, come on, what's the physical meaning of the gradient? It's a vector which points where? Which minima? No, this vector doesn't point here. If you start, it doesn't point there. It's a direction. Okay, that's the thing. We're almost there. So no, it's not a product of structure. Okay, in 2D. Right now I wrote it in 3D. Right now we have an example in 2D, right? So that means that we have W2 and W1. So I'm asking you, in this case, I take a look at and this point, And I see that actually gradient is here, right? Because it's moving there. We right now know that it will move towards gradient. What is the physical meaning in this case? What's special about this direction? Why not move here? Why this point, again, for instance, it's not a product, it's yes, but why is here and not here? Come on, Naim, Naim, do you know what's the physical meaning of the gradient? It's the direction of the steepest slope. Gradient always points to the steepest slope. It's pointing to, I would say, local. You cannot say local maximum or local minimum. It's actually pointing to the local. If you have the directions around you, it will go towards where the slope is the steepest. It doesn't have anything to do with the global minima, nothing like that. Even local minima, it's not true. So it's really not true. You just look around the point, and actually you can see here, for instance, you see why it's moving there, because the slope there is actually all these black lines. You should understand. Do you know what the black lines are? They're called isosurface or isolines. It's the same thing that you have on the topographic map. It's actually lines with the same height. So therefore, actually, if you move along the line, you do not change your height. So you're basically going at the same height level. So, and what's important, if you look at the steeper slope is the slope when your distance between next lines, black lines, is the smallest. So it's another way to draw it. Gradient always points to the direction of the steepest slope. It's something that you really need to remember. And therefore, when you start here, it has nothing to do with here. You see this isoline, and your actually gradient is perpendicular. All these lines are perpendicular to the black lines, just from the physical point of view. So, okay, now we figure it out. So therefore, our gradient descent will always try to move towards the deep and deeper point. And of course, if we have a multiple minima, we may stuck there. But in general, that's why you usually converge somewhere. So because you always go somewhere and stuck there if you have a minima. Okay, important, and I'm surprised a little bit. So, with that in mind, it would be very, very interesting to yes, let's do that. Let's actually, because I would like to show that I think it's important, and we have exactly enough amount of time to do that, to play a little bit with give me a second, just skip. Yes, I want where exactly what I want to do that. I would like to do it here. So let's take a look at our cost function if we assume binary classification. And our function, if you remember it from the previous one, it looks like that, right? So also what we know if we do binary classifications from the machine learning point of view, we know that our output value will be subjected to the sigmoid function. Remember that? Again, nothing new. That's all you have already seen. So let's denote this one as we usually do. Z. Okay. And now it's important for us, because when we do a training, we are looking at the cost function at the last, like basically this J function at the end, and we know that we need to be able to calculate the derivatives or gradients, because that's exactly what gradient descent does. So right now we actually we're disconnected. Gradient descent was on one side, neural networks were there. So right now we're merging them because we're actually using gradient descent to train our neural network to search for the weights. So that's where they're finally getting connected. So and now my question would be, okay, I call it J or I call it L, doesn't matter for now. What would be the derivative of L over, let's say, weight number 1? Right now I try to simplify. So right now what we have our perceptron. If you remember, hey, let me make it a little bit larger. So we have Z here, then we use sigma Z, and it's our output. And our Z is actually WT x plus W0, right? Cool. What would be the derivative of our L function in relation to W1? Do you see why it's a little bit problematic? Because actually in this expression here that you see, we have no weights at all. We have just our predictions and true values. So what we can do that in this case, we can use, we can use so-called chain rule. Again, I think you should be familiar. And we can take first derivative over the y prime, because that's something. Y, okay, and multiply it by derivative of y and y prime versus our weight. Is it clear? Basically, it's question is why I do not take derivative of, I take it y hat, sorry, not y prime. Why do I not take derivative over y? Again, because absolutely right, because y, it's something is given to us. We do not predict it, so therefore they do not depend on the weights. They exist. So, okay, we can do one more split here for simplicity. We can say that this would be equal to do you see that? Basically, we split this one. We say, okay, we do not do directly the derivative. We first of all take a derivative related to the z, and then take derivative over that. Okay, so should not be a problem. So that's important. So that's the fact that we can split our derivative of the loss function. That is extremely important for gradient descent into the three smaller derivatives. And now let's calculate them. Let's really do that because it's not so hard and it's very beautiful. So first of all, let's start with this one. So what is our derivative over y? Let's right now remove all the sums and completely ignore that we are summing. We're just really interested in what's happening inside, because again, that will be summation here. It's for all points, right? So we kind of right now consider one point only, x and y, and working with that. So what would be derivative of y log y? Yes. We still have a minus because I would like to have minus from the beginning, but yes, it would be actually y divided by y hat, right? And what we will have here it will be minus, but then when you will take derivative of minus y, this one minus will go. So there is a minus. It's plus. So yeah. So basically, I just skip one step. Okay, nice. Okay, that's not bad. Let's take a look at this one. What will be derivative? So first of all, that's how it looks like. Okay, so basically I replace our y hat by the expression via sigmoid function. So, and again, from here, actually what we will get, it's a little bit, it's not so complicated, but I will just copy it from my note. And you can see like y squared, because it was -2, it's like then was -1, then it's -2, and then we have a derivative from the bracket. So it's, again, this is obvious. Nice. Do we see a way to actually simplify it? Okay, you don't see this because I need to write probably for you just to remind you. Is it plus here? It's plus, yes. This function. Do you see something cool about the expressions that we have? Yeah, basically, again, if I will just replace, if I will just do simple mathematical things on that, give me a second. So, okay, what do you mean sigma square? We don't want to have a sigma at all. So what's the bottom? No gradient at all. Okay, what's the denominator? Do we see that actually it's, first of all, do we see it here first? Because 1 divided by this in square, it's actually that. So maybe, again, this is not exactly, I understand why you say sigma. It's actually sort of would be like that. And also we have basically in this case also still this one, and we can, believe me, we can actually easily change it and get this result. Verify if you want, but that's true. So then you basically, what you're doing, you just plus 1 and take another y hat, and then after simplification you will get exactly this. Okay, that's really nice. And finally, and that's the beauty of this particular function. And finally, let's take a look at that. Who would be the fastest to actually tell me what's the derivative here? Come again? No. No, we take derivative by w. Okay, forget about t. T is basically vector formation. So think about how this will look like if we look at that from the point of view, kind of something like that. And plus w0. Take derivative by versus w1. What would be what we will have? X, exactly. That's our derivative here. It's x. It's nothing more, nothing less. So therefore, and that's a beautiful thing, that whole our derivative here will be equal, again, you write it down, to so this quite complicated cos function, that's why it's beautiful, that's why it was introduced before machine learning, it's actually a function that's used in statistics, gives us extremely simple derivative. And of course, when we have not one d case, but multiple d, all our elements of our gradient will have a similar style. So it's extremely easy to calculate derivative right now, despite the function itself has logarithms and so on. So that's important. We right now remember that. We right now remember that we can use very, very easily find a derivative. To be honest, if we do the same from mean square error, we'll have much more complicated result. So despite this function despite the fact that this function looks strange, it has very nice derivatives. Okay, remember that, because in a couple of slides that will be important. So we wrote it down. And now I would like to ask you a question. There was already answer, but Let's take a look at this function again. Just function itself. It's j is equal to, now we look at that fully with summation. Oh, sorry. And now I would like your attention here. Derivative. And also, I would like you to pay attention to the sum. And m, it's a number of points. What, in your opinion, can be a problem with this particular approach, with this gradient descent? When we will see a problem? Any ideas? That's the thing. Okay, that's the thing. That you are on the right way. Imagine that I have a million points. And that's actually normal for the data sets to have a million points. It's nothing, basically. For now, it's nothing. And now, for each iteration of gradient descent, we need to calculate 1 million derivatives. And we need to calculate the sum. And it's slow. That's a problem. It's really a big problem. So calculating derivative for the entire data set is time consuming. And now actually I'm skipping one part that you will see on the next slide. We actually calculate the derivative only for the last layer. We didn't touch whole neural network for now. So, and it's already kind of sophisticated. And of course, in this case, you need to have a lot of memory to store all these million data sets, points, together with derivatives. Or if you don't have enough memory, you need to store it on the hard drive and basically have an enormous penalty for reading out. So what is the solution here? And actually there is. And you probably already know the solution. Have you? Can you guess the solution for that? You actually use that during the training. One of the parameters that you use during the training on the practice actually helps. For gradient descent, we need to compute derivative for each point in dataset, right? For one iteration. So there is actually a suggestion to use so-called stochastic gradient descent. And therefore, in the stochastic gradient descent, we compute this derivative for only one point and then immediately update our weights. So we do not try to kind of compute everything. We just do it point by point by point. Every time, of course, we have a quite random direction, but on average, we actually will go towards the minima. So that's why. So basically, you do not do summation at all. You take the point, you see which way you need to go change the weights in order to minimize your loss function, and then go there. So it's not effective, but at the same time, you update it much more often if you do not wait for 1 million specimens to compute. So, and therefore, of course, there is a middle ground. It's called mini-batch stochastic gradient descent. And when you compute these derivatives or loss function itself for just some of the points, and then you update your weights afterwards, and then repeat it over and over again. Why this is faster? Because our modern computers, and let's say NumPy in particular, or TensorFlow, they can do so-called vectorization. So you can do mathematical operations on the vectors with the same speed as on the scalars, because everything is done in parallel. If you have a lot of data, if you have a lot of points in your data set, you will not be able to fit into the RAM, and we already mentioned that. But at the same time, if you do it one by one, you're losing this opportunity, you're losing this ability. So therefore, there is some hyperparameter, which is called batch size. It's actually batch size or mini batch size, depending on the terminology. How many specimens, how many points do you process simultaneously before the next update? So, and if you look actually at the model.fit that we used, the comment, you will see that you have here input values, output values, and the third important parameter is called batch size. That's exactly the amount of specimens that you will, or points, sorry, that you will process simultaneously before the next update of the gradient descent. So it's called batch size here, but actually by definition it's mini batch size, because batch size is the total size of your data set. So if you say your batch size is 1, then you're doing stochastic gradient descent. If your batch size is equal to whole data set, you are doing the classical gradient descent. But when you use some intermediate values there, you, in this case, working with mini batch stochastic descent. And of course, in the batch size, due to obvious reason, usually something like, and so on. So it's actually power of 2. You will see it all. And we actually used it power of 2. I don't remember which number exactly. And basically another parameter is epochs. It's epoch, and I had the question during the practice. So if you do this batch, we say do mini batches, how it's interacting with the amount of epochs. Epoch, by definition, I actually looked at that. It's when all samples processed, you start a new epoch. So epochs are not related to the number of updates of the weight. It's basically amount of time you loop through whole data set. So therefore, you can have like 20 epochs, and inside of each epoch, you will have the mini batches. So there is a very important parameters like X, Y, batch size, and epochs. Everything else is absolutely kind of useless at the beginning. So just keep it in mind. Can we improve it a little bit more? We already have a nice trick in our sleeves. We really can do these mini batches that are vectorized, they're running in parallel, super cool. So yes, we actually can do even better. We can dynamically update the learning rate. Remember the learning rate thing? Of course, we actually see even on this video, when you're going closer to the minima, your distances become smaller and smaller. So it doesn't make sense actually to, let's say, run with the same learning rate. So you can actually decrease it gradually, otherwise you will jump over. So therefore, there is a way to dynamically update the learning rate, and there is an adaptive gradient algorithm that does that. Another way to do that is used in a so-called RMS prop algorithm. You also, what you can do, you can take into account previous update, because in each step right now, when we consider gradient, you completely lost information about the previous gradient update. So you jump it and you forget previous point. You can actually track that and create so entity called moment that basically track how far you jump it. It's very similar analogy with the physical moment. And you can use just Adam optimizer. If you remember, we used this line to create an optimizer, and we used Adam. And Adam, it stands for Adaptive Moment Estimator. And this is the best optimizer that we right now have, because it utilizes all of these techniques. And it's much faster and much in training in comparison with all previous ones. So there is some comparison in the internet. You can take a look. And always use Adam, unless you have some specific goal to, let's say, try separate RMS prop or momentum. How does it work? And that's basically we're close to the end, because we need to understand how does it work for the whole neural network rather than for just last layer. And it's called backpropagation. And do you remember that? It's basically what we did on the previous slides. We derive the derivative on the last layer and say, okay, right now we can split it. Now we need to do that for each hidden layer. And that's maybe a little bit more problematic. So let's take right now, I will take, let's imagine that we are not at the end layer. We end some hidden layer. So, and we have our, we call last layer, and we have hidden layer. So let's imagine now this is expression for hidden layer. We can obviously calculate this for this hidden layer. It's not a problem, because it's actually the function. This is, again, that would be weight. It will be just x, right? Remember, we did that. This one will be also not will not be a problem, because it's actually derivative of sigmoid or tangent, doesn't matter. So we can do it locally. It's not a problem. The problem is actually with this one, because we try to understand how loss function that is actually happening here is affected by the weight that is changed here. So we have one intermediate layer here, and it's super annoying because we cannot right now clearly do the same thing that we did on previous slide. How to process that? If you mathematically approach that, so what does it mean? We need to actually take a look at how each, if we have a couple of nodes here in this layer, how each of these nodes getting affected by the change in our input. So output, sorry, we have y here as output of our hidden layer, and of course it's affecting everything that is going from here. So we need to take a look at how loss function depends on the change in y hat through these layers, and we can sum them. But then a trick happens. If we take a look, let's say, how this particular loss from this output layer getting affected by the change in y hat, we can also do it as a split. We can take a look and say, okay, it will depend, so let me draw it somehow, that as a z of last one and j of the last one. First of all, let's take a look at this one. So what we can say, this is quite obvious how to calculate. It's basically our input to this layer, how it's affected by the change of output. So, and we know that actually it's a linear combination, basically. Okay? So we have no problems with that. I mean, try to bear with me. I don't want to go into deep mathematics. Just, this is not a problem. Not a problem at all. What's with this one? So this is actually, it's crazy. This is a change of the loss function at the end of our neural network in relation to change of the z that actually comes from here and getting computed like that. And if you remember, we actually already calculated that. This is already that we have. This is expressions that we have for the last layer. We just can replace it. Therefore, by knowing derivative of the last layer, we more or less automatically know everything for the previous layer. We just need to locally compute these two factors, that's just locally, they do not interact with the layers beyond, and take something from the last layer and back propagate it to the previous one. And then if we took another layer, we actually just back propagate this one to here and this one to here. So we do not need to recompute anything if we want to understand how small change of the weight in this layer affects the loss function. We already have all expressions, and that's therefore why it's called back propagation, because we don't care about the information here in the beginning of the neural network in order to find how whatever layer is a change in weights in whichever layer affects the loss functions. We just need to know some derivatives on the way, and that's all. And therefore, the neural networks are very cool because they can be effectively trained. All the derivatives are very nice, continuous derivatives if you use nice activation functions. And that's why you don't have a heaviside. It will break everything. And therefore, how you can really, really easily train them using just basically mathematics. So I hope that this particular transition is clear. If it's not, I really recommend you to just take a look at YouTube or maybe into the lecture notes, because to do it properly, I need to write much more, and I don't want to spend time on that. But the idea that you need to understand the beauty of all the thing, that the derivatives that appear when you calculate the effect of this weight, actually, it contains a derivative for this layer, for weight on the second layer, and you can back propagate it. It's amazing. So, and now we basically know everything. For the training, from the theory point of view, we really know almost everything. So probably a little bit of the next lecture we'll spend on the training test, and then we can discover new architectures and new approaches how to really do that. So mathematics will be a little bit heavy on mathematics for the support vector machines, but then we will just play with the convolutions and so on, because we right now have all fundamentals. So right now we basically cannot decide on architecture. We still don't know exactly how to do that properly, but we can define training set. We know how training happens. We can understand what's test set. We know how to evaluate our model from the beginning of this class. And finally, we can enjoy our good model. So yes, I will not go for the support vector machines today, because this is where it's getting, let me skip it, quite complicated. we learn a little bit things. Yes, and what we learned today, basically how to understand if our predictions are good enough. Now we know different loss cost functions for classifications and regression. We understand gradient descent and its variation. Yes, and that's for now all. Support vector machines are quite mathematically heavy, but they are cool. And support vectors machine, it's not exactly deep learning because it doesn't have neural network architecture, but it uses very similar regressions, and results can be very easily visualized. That's why I like them, and they are really powerful because, again, this is more than 1 million papers. If you say support vector machine mechanical into Google Scholar, this is very popular topic. It's very robust system. It's much more robust than neural networks. Yes, unfortunately, it's not working well on large data sets, but we discuss it. So for the lecture, for the basically new things that you learned today, it's over. So I would like to keep the changes. And now I would like to, since we have a little bit like 5 minutes more, I think, to update you regarding the home project. We uploaded the final version of the home project. We uploaded, if you already had a chance to look inside of Ilias, some previous version, but we updated it a little bit in order to add visualization. So take a look into Ilias home project, I think it's called, something like that, and then you will download that. It will be very, very clear what's happening. But actually, it's based on the paper that we published recently. And come on, I forgot to download. Okay, in this case, unfortunately, I cannot probably draw it here, but it doesn't really matter. So what we did, and I already showed you during the practice, we did these materials when we changed the geometry a little bit of the beams, and due to that we have a very different properties together with Gerrit and Naim. Basically we did first of all prediction of the properties, it's this part, and also we did generation of the lattice. This is the second part, and right now you are not prepared to do the second part, but you are more than prepared to do the first part. So let me explain the concept itself. So you can define, again, this is the theory, we can skip it, yes. You can define each curve using so-called Bézier curves. Are you familiar with the concept of Bézier curves? No? There was a guy with a surname Bézier, and he actually was a designer of the cars in the 1950s. And he was the first who designed these smooth, nice car bodies. Because previous cars, if you remember correctly, were very, very not so fancy looking. So, and he invented and then used so-called Bézier curves. It's the special types of curves that are recursively defined. And in order to define a curve, you just need to know the coordinates of these points, 6 points. Okay, so exactly what we did, we say, okay, now we will put the points more or less equidistantly, and then use the y coordinate of the points as the input of our neural network. So we used not 6 of them, but 5, because we always wanted this to be 0, 0. So what happened in this case, if you're interested in the definition of the Bézier curves, you can look at that. But we can construct so-called metamaterial from that. So basically, this is one Bézier spline, this is a mirror Bézier spline, and then you can tile them to the material. And at the end, due to that, you can have basically different geometries. You can skip this as well. And then what we did, we train a very simple neural network. So you have 5 inputs, right, into your neural network. You have a fully connected, what we call dense or fully connected, the synonyms, layer with, okay, we use layer normalization, it's not important, and Licky-Relu function, you remember that? Right, so kind of if you forget about ln, so we have one layer with 5 input layer, 50, 50, 30, and 1 output, and yeah, so we're looking only on the left one. So we have output, and you see we don't have a sigmoid here because our property range is actually continuous more or less. So we have -5 or 1 or 2. So we predict Poisson ratio. And therefore, and then we basically train that. And we get a very nice match. And at the end, we show that we can predict by knowing just 5 numbers, we can predict very nicely the resulting Poisson ratio of these things. Of course, later we do, in order to make it more solid, we do a little bit more sophisticated stuff with generation, but we will discuss it a bit later when you will be ready for the generation. But for now, basically what that home project is about, we provide you with a data set of the Bezier curves and with the resulting Poisson ratios of the metamaterials. You can visualize some of them because we already have some functions there for you just to play with the geometry. And we're basically asking you with instructions to write a code that will train neural network that will predict the resulting properties based on the 4 or 5 coordinates. That will be a home project, and we would like to see how you progress with this home project. It's one of the 3 home projects that you will have. Right now, what you need is basically to implement that and just upload it into the corresponding folder into Ilias. And yeah, then if you will be very interested in that, if you will pick this project as a main project, then you need to write a little bit more as a report, for instance. So kind of how training procedure affects that, how a number of layers affect this training, what's the learning rate, and so on. So basically, because at the end, we would like to have one full report from you from one of the projects. This is one of the projects that you can do that, but you can also wait, or you can propose your own project as well. So yes, and on that note, again, I will end this lecture, and I hope that you learned something new from here, and I hope to see you on Thursday and then on Monday. Thank you. 1, 2, 3.